they are sharing some information that that bring the system to the synchronized state. Okay, so synchronization is a concept that was introduced in the 17th century by Christian Huygens, when he observed that some clocks hanging in the same wooden beam could synchronize their pendulum clocks in phase or anti-phase, even when they had slightly different frequencies and when they had different initial conditions. Synchronization actually appeared in many natural systems and is of a broad interest in different fields. Some examples of synchronization, spectacular examples, I think. One of these is the flashing of fireflies that at the beginning they have their own period. They start flashing during the night randomly when they think they are ready, and after a while all of them start to flash at the same time. So here you can see a snapshot of the maximum intensity of this flashing. Other examples are in civil engineering. This is the Millennium Bridge in London that I will explain in a bit more detail in a minute. And also in the brain, where neurons can emit electric signals and can synchronize different areas of the brain, even when these areas are one far from the other, and they can synchronize without delay. So the outline of my talk is this one. I will introduce the concepts of crowd synchrony and dynamical quorum sensing. I will explain you the main characteristics, and I give you one example of each one. Then I will introduce the semiconductor lasers, that is the system we choose to try to reproduce these two transitions to synchronization in star-coupled configuration. So we will show how we can obtain dynamical quorum sensing and crowd synchrony in this system, and we will study different parameters of the coupling and also the time delay. Then I will show you recent work we published with Eduardo about double transition to synchronization. I will give you some ideas about the analytic calculations we did in this work, showing that our equations can be rescaled to obtain two different approximations to these two transitions to the synchronized state. And finally, I will show the main conclusions of our work. To fix the ideas, I want to show this very simple slide, because what I want you to I want to give you the idea of what is crowd synchrony and what is dynamical quorum sensing, what are the main differences, and how can then we go with these ideas to the system of semiconductor lasers. The case of crowd synchrony is a smooth increase of a certain order parameter, a certain parameter that measures how our system is synchronized, from a low level of synchronization or no synchronization to a high level of synchronization with this smooth increase in the synchronization of the system above a certain critical number of elements in our system. We have a system of many oscillators, we increase the number of oscillators in our system, and above a certain number of oscillators appear in synchronization. Dynamical quorum sensing, on the other side.
Why are you scaling on your left field with the y-axis with them to 1.5?
Because if not, this order parameter has, due to the small number of elements at the beginning, it has a shape of this form.
It's a little, is that artificial or arbitrary? Or?
Well, it's not.
What is the order parameter?
The order parameter is, in the Kuramoto system, is the sum of complex exponentials of the phases.
And you scale that with the square root effect?
Yeah, to avoid these small size effects that appear.
To avoid or to mask?
No, because the idea is that this part is not related to synchronization. So in the case of dynamical quorum sensing, the main difference is that below a critical value of the density of elements, here it's not writing, but it could be the density or the number of oscillations in our system, the oscillations and synchronization occur simultaneously. Below a critical value, there are no oscillations, all the oscillators are in the quiescent state, and above the critical value, it appears synchronization and also the oscillations of the system. So,
why is this called quorum sensing?
I will come in a minute. Let me show first what is crowd synchrony. Crowd synchrony was observed for the first time in the Millennium Bridge in London. This is a pedestrian bridge that was opened on June 10th, 2000, but it was closed 2 days after the opening day because excessive wobbling in the transversal direction. They observed that when a large crowd of people were walking in the bridge started wobbling on the transversal direction, something that the engineers didn't expect, something that lasts 1 year and a half to fix, spending around £5 million. This effect in the subsequent research that they did showed that a large number of walkers synchronized their steps. At the beginning, they were walking each of them with his own rhythm and frequency, and these walkers start to become more and more synchronized. More walkers were walking with the same rhythm, and it made the bridge to wobble in transverse direction. They also found that exists a critical number of pedestrians for this wobbling. This wobbling doesn't appear for a small number of pedestrians walking in the bridge, but when the number of people walking is large enough, it appears this synchronization. Few years later, it appeared this explanation, but by Strogatz et al., where they gave the name of crowd synchrony to this effect of synchronization in the bridge. What they did is to simulate. They did a model of the bridge and the pedestrians, where the pedestrians were represented by Kuramoto-like oscillators, coupled, all of them only with a bridge represented by a damped oscillator. So in this case, all the pedestrians had different natural frequencies with a certain distribution of these frequencies, and the bridge was in the resting steady state. And they also consider it, as can be understood, instantaneous coupling. The kind of results they obtained were of this shape. That after a transient time, this is the phase in the color code. You can see that the phase of these Kuramoto-like oscillators, after a transient time, all of the oscillators become synchronized, and also the bridge, the amplitude of the bridge, become to increase. So this kind of systems lead to these effects that for the normalized amplitude of the bridge and also the order parameter, when we increase the crowd size, the number of pedestrians walking in the bridge, it appears this synchronization above a certain critical value. Okay? The amplitude of the bridge is at 0 for low values of the crowd, and at the same time the bridge starts wobbling and people start to be more and more synchronized. As I said, the parameter is the sum of the complex phases of the oscillators, so it means that here you have more and more elements synchronized in the system. So on the other hand, the quorum sensing is
There is transparency. I mean, if you go to the second, I mean, if the square root of 250 is more or less 15, right? And that's more or less the same side. So it's a little bit confusing to me because the maximum is basically the factor by which you multiply the R. So
here?
No, the other one.
No, in the second. Into the one.
Well,
So it goes from
if
0 to 1, basically.
If you this sort of parameter here has a maximum value of 1.
Yeah, that's what I mean. But basically, at 250, the value is the square root of that, right? So basically, it's 1 for the Kuramoto of the parameter. So I don't really see why you use this. The correction.
Well, this
So you say for the beginning because it's
Yeah.
a curious synchronization in that case.
Yeah, this is actually not synchronization. It's actually a small size effect.
But this is a big size effect.
No, I mean for small values of n.
Yeah.
Yeah, so maybe it's more common to show here the value of 1, the normal order parameter 1. Okay. So those are the main ideas behind the crowd synchrony. On the other hand, quorum sensing was introduced in biology to talk about the production and release of signaling molecules between different cells using the surrounding medium. This quorum sensing can be used to induce synchronization in a colony of cells. For example, in this case, was used oscillators, synthetic oscillators of gen expression that showed for small density of oscillators in the system, all of them evolve more or less independently, each one with his own phase. And for large density of these oscillators, all of them become synchronized. In using this quorum sensing, it was shown that cell colonies, or yeast cells, bacteria, in this case E. coli bacteria, can use quorum sensing to synchronize the activity, the production of a certain protein, when the density of these bacteria is large enough. So what can be seen for certain proteins is that for a low density of these bacteria, the activity, the production of these proteins doesn't occur. So we could see only black screen if we are looking at the fluorescence of some protein that we are interested on, and above a certain density of the bacteria, we start to see synchronized production of a certain protein. Here snapshots of a sequence of this production, so we can see that they oscillate clearly and produce this protein synchronous. So this dynamical quorum sensing, however, is not does not only occur in bacteria and in biology. Recently, it was shown that chemical oscillators can also show this dynamical quorum sensing. Taylor et al. Used a system of Belousov-Zhabotinsky medium with small catalyst particles, that in our case will mean our oscillators. They put these catalyst particles inside the Belousov-Zhabotinsky, and these particles start to produce this reaction in the Belousov-Zhabotinsky medium in its surrounding, changing the color of the Belousov-Zhabotinsky from red to blue. So in this case, what they consider is that each oscillator, each catalyst particle, have different frequencies related with the diameter of the catalyst particles, and of course, without the catalyst, the Belousov-Zhabotinsky medium is in the steady state, so it doesn't oscillate, and of course, instantaneous coupling. So what they found is that using the Belousov-Zhabotinsky with the catalyst particles, they could change the how sharp is the transition to the synchronized state depending on the steering of the system. They used steering to move the catalyst inside the Belousov-Zhabotinsky medium. So they measured also the intensity of the red color, that means the production of one of these chemical elements that produced in the catalyst, and also the electrical signal in the Belousov-Zhabotinsky. So they had measured for the oscillators and measured for the common medium. As you can see here also, there is a certain relation, that certain similarities between the case of the Millennium Bridge and this case of the chemical oscillators. They performed some experiments, and they also found a model for these reactions given by a dissipative coupling between the chemical populations. What they found is that when they measured the amplitude of the electric signal in the Belousov-Zhabotinsky medium, depending on the density of the catalyst particles and the stirring rate, they found a sharp transition to the synchronized state from a quiescent state where the Belousov-Zhabotinsky had always the same color to a synchronized state where they measured this electrical signal. As you can see here, this is a section of this figure. For large stirring rates, they found a sharp transition to the synchronized state with large value of amplitudes at a given critical density. But for a low stirring rates, they found that there was a smooth transition to this synchronized state. So in this case, they found that these two transitions can be controlled by this stirring rate parameter. But okay, those two examples are similar in some sense, but the question is, are those really examples of a common and more general behavior? Can we find this behavior in other systems, maybe completely different? So our idea in this case was to use semiconductor lasers because they had many advantages, to try to find crowd synchrony and quorum sensing and try to describe with the magnitudes of the semiconductor lasers when crowd synchrony and when quorum sensing occurs. So
when you mean the general behavior, you mean exactly what? That there is a transition, a continuous transition changing the system size, and that there is a discontinuous transition in the other case? When you have oscillators, or what exactly you mean a general behavior?
I mean, from one side, if other systems can show these two types of transitions, on the other hand, is there any relation between these two types of transitions? And if yes, what are these? What do the systems so peculiar to show these two transitions, or not? If it's something more general that can be put in the same type of behavior, in the same type of transition, and it's something that you can understand only with one model, if you want. Other questions from here is, for example, if it's possible to synchronize, to show this behavior in other type of coupling topologies, for example, or because here I showed that this is a star coupling topology. You have a common medium, you have the catalyst in this case, the pedestrians in the case of the bridge. Is it possible to show these behaviors in other topologies? It's not simple. I don't know if it's possible to change the topology using these chemical oscillators, but it could be possible, for example, using semiconductor lasers. Or there are other systems with other coupling topologies. Is it possible in these other systems show these two types of transitions? So all of these questions came to our mind after reading these two works. So the idea was to use.
The previous example, is this two-dimensional or three-dimensional?
This one?
Yes.
It's three-dimensional. There are three populations of chemical reactives. So, but well, you have different equations for the catalysts and two other equations for the Belousov-Zhabotinsky value. So, for who don't know a lot about semiconductor lasers, I would to show some ideas of why we choose semiconductor lasers, why we study semiconductor lasers. So, this is okay. Okay. This is a semiconductor laser compared with a penny from the US. Those devices are broadly used in many applications, as you probably know. You can find semiconductor lasers in printers, mouse, CD and DVD recorders and readers, because they have a small size, good stability performance, robustness, and low cost. And they cover a large range of optical wavelengths. So they are very interesting to study, to find new applications, and different types of dynamics, despite they are very stable, can be induced in these devices. For example, when you use a feedback and you reinject the light of the laser again into the laser using, for example, an external mirror. So kinds of dynamics like low frequency fluctuations can be found, and other different but also have been studied with lasers with modulation, also for optical communications that are very interesting. But especially, and in our case, we are interested in to use semiconductor lasers because they can be synchronized, and this synchronization is possible using several of these semiconductor lasers. For example, in this case, I show an example of 3 coupled lasers in a chain, with a central laser in the middle and 2 lasers in the in each side. So there are other possibilities with arrays of lasers that can contain up to 40, 50 or more lasers. That could be a good option to go beyond these small networks of 3, 4, or 2 oscillators. So what we did is to study a system of M-coupled semiconductor lasers in a star coupling topology, coupled all of them through a central element that we will call the hub laser. And between this hub laser and the star elements, we put a time delay in the coupling due to the finite time that takes the light to go from the outside of the star to the hub and come back again to the outside of the star. So to do a similarity with what we had in the case of the Crowd Synchrony and Quorum Sensing, we used our semiconductor lasers as oscillators. Keep in mind that we had pedestrians in the case of the bridge, chemical oscillators in the case of the Dynamical Quorum Sensing. Each oscillator have different optical frequencies with a Gaussian distribution in our case. So they have differences between them. These star elements are not exactly the same. so we are considering certain heterogeneity. And the hub laser in the resting stable steady state that we did this using a pump current of the hub laser below the solitary laser threshold. It means that without coupling, the hub laser is not emitting coherent light, it's off basically. And as I said, we use coupling with delay. So,
may I ask a question? I'm not really clear about the rationale of these equations. You don't scale the coupling factors, right? So that means for 100 incoming lasers, you have 100 times the inputs to the fluid center device, right? Which will then certainly operate under very different conditions. The other thing, certainly, the other problem is even bigger. You assume that each of the outer lasers would receive an input that is independent of the number of connections. How would that look like? So how would actually an experimental configuration look like that would be able to reproduce these equations?
Yeah, for example, you could use an amplificator.
But that would mean, for example, you would even need separate connections for the incoming connections and for the outcoming connection. And you would need to adjust for every added element. You would need to adjust the amplifier for each of the outer elements, right?
Yeah. And it's really difficult, if possible, to do it experimentally with semiconductor lasers. Because these problems, it's difficult to adjust carefully all the time delays, for example, to be the same in each path. So as you said, if you use an amplification, you have to use different paths for this direction, the light coming in this direction, and the light going on the other direction, which means you have to adjust 2 times more paths to the same.
So what was the motivation then to use the laser equations?
So the idea was that first, if it's possible, it could be very interesting to obtain large output coherent light from.
Well, but we just realized the experiment is actually rather unrealistic. And if it's about the kind of behavior, I think more generic oscillators like Stuart Landau or whatever would probably be more generic.
Well, yeah, probably with Stuart Landau we could do something similar, but Stuart Landau are more generic, so in this case we were looking for something a bit more applicated to stimulate discussion about this topic and discussion about if it's possible or if we can go one step beyond and do it possible. If we obtain large sorts of coherent light from this configuration, why not try it? Why not spend time to try to do it?
Theoretically.
I don't understand what is omega naught. Shouldn't it be omega h?
Well, let me
omega
explain a little bit the equations. If you agree, maybe you can continue. So the equations are a generalization of this work done in 2006. Ingo Fischer and co-workers, where they used 3 of these semiconductor lasers, as I explained before, a central laser with two lasers in the outside. So in this case, it's a generalization of the model they used. Those are the equations for the star lasers. This is the slow envelope of the complex electric field of the star lasers with a detuning frequency with respect to the central frequency that we call this central frequency omega naught. Okay. This is the term for the solitary laser that is commonly used. The term for the coupling with a constant coupling K, the term that comes from the electric field of the hub laser with the time delay tau, and the phase difference between the light that comes from the coupling and the electric field of the star lasers. And a term of Gaussian white noise, non-correlated, representing the spontaneous emission of the semiconductor lasers. And the other equation is for the carrier number of the semiconductor with a pump current mu and the term of spontaneous and simulated recombination of carriers. So for the hub laser we have mostly the same terms, the frequency of the hub laser, the term for the solitary laser, the coupling with all the other lasers in the system, that is the sum of all the delayed electric fields from the star, and the noise term. And notice that we have used basically the same parameters for all the lasers, except for the frequencies of the star lasers that I said in our case have a Gaussian distribution of frequencies. The frequency of the hub, that in our case we choose the central frequency of this Gaussian distribution, and also important, the pump current of the star lasers is the same for all the star lasers, and this pump current is different from the pump current of the hub laser. As I said, we use a pump current for the hub laser in the resting stable steady state, which means a pump current below the solitary laser threshold, and this for the hub. And for the star lasers, we studied the two cases: what happened above the solitary laser threshold and below the solitary laser threshold. So, I'm going to your question. This omega 0 is the central frequency that can be 800 nanometers for the wavelength, and tau is the time delay. So, first of all, let me show you what happened when you use a pump current for the star lasers above the threshold. When the star lasers are pumped above threshold, we can see something different depending on the number of lasers we are using. Here, increasing the number of lasers. This figure shows the intensity of each laser. Here, 10 lasers, and in the color code is the intensity of these lasers. And as we can see, for a small number of lasers, each one revolves independently. Here, those oscillations are from the relaxation oscillations of the laser due to the noise. And also for give you a general idea of which frequency has each one of these 10 lasers. Here we show the frequency with the theoretical Gaussian cumulative distribution. So what happens if we increase the number of lasers in the star? So for example, when we put 25 lasers in the star, we can see that some clusters of synchronized lasers appear. Here, as you can see, there are some lasers that become more synchronized than the others. Here, those lasers are not synchronized except at some point, but when we keep increasing this number of lasers, we go to 30, the size of these clusters, these synchronized oscillators, become larger and larger, and for large enough number of lasers, most of them are synchronized. And keep in mind that we are using time delay, so this figure means that they are synchronized at 0. So it means that they are oscillating at the same time, even when they are the time delay between one outer oscillator and the next one is 2 tau, because the information has to go through the hub. So to better show how appear this synchronization, we use the coherent intensity as a measure of our order parameter and see what happens when we increase the number of elements in our system. So tell you that the coherent intensity is the sum of all the electric fields modulus squared and averaged over a certain time window. Okay, so what we see is that for a small number of oscillators, the value of this coherent intensity is very small. Each one is evolving independently, almost independently, and at a certain point, the coherence starts to increase, and this gives the region where these clusters appear, okay, up to a certain value where most of them are in the cluster and they are mostly synchronized. Depending on the coupling strength, this transition will occur for one value of the number of lasers or the other. So for a coupling strength of 10, we cannot see in this range of the number of lasers where the transition occurs, but for 20 it occurs here, for 30 around here at some point. But what happens if now, instead of studying the star lasers with a pump current above threshold, we study the star lasers with a pump current below threshold?
One more question. When you say you get now coherent superposition of the fields, can you go one slide back? Why don't I see that in the distribution functions of the frequencies?
This is the solitary frequency, the frequency of the solitary laser.
What is the line and what are the points?
Okay, the points corresponds to the frequencies, the optical frequencies of the solitary lasers we used for the simulations. Okay, and the black line
before coupling.
Before coupling. Yeah. Sorry. Yeah.
So they are the parameters of the equations. This is the parameters you put in the equations. This is the what you are putting there.
Right.
It's not the dynamic, it's what you put it.
Yeah. So what happens if we decrease the pump current below the laser threshold? First of all, means that the solitary laser is turned off. It's not emitting light anymore. But when we couple more and more lasers, due to coupling and the small contribution of the noise, they can turn on because the effective threshold of the laser decreases due to coupling, and they can turn on due to these small perturbations. So this is what we can see here, that when the pump current of the star lasers is below threshold, this sharper transition occurs, also at a given value of the number of lasers, in this case. And also the coupling strength modified where this transition occurs. So at this point, I think we can directly compare what we obtained for the semiconductor lasers in the case of the concurrent above threshold with what happened with Crowd Synchrony, this smooth transition, and what happened when the pump current is below threshold with the Dynamical Quorum Sensing.
Let me back to what Dingo said. I mean, the coupling to the central hub is increasing a lot, right? I mean, what happens if you do exactly the same thing but you normalize the coupling to the hub? Is the same is happening qualitatively or not? Because my feeling is that it's not going to happen.
No,
especially
not
right
at all.
now. And the other thing is if you substitute the central hub by noise, okay? So you put a common noise that drives all the other ones, and you just modify the intensity of that noise. Something similar should happen, right?
Right.
I mean, you don't need to do these things. So somehow, I mean, there is not a collective effect. I mean, it's quite artificial, right, in this setting.
The main idea behind this collective behavior, let me say it in this way, is that the hub laser doesn't have his own dynamics. The hub laser is pumped below threshold, so he have to wait for what the others say. Depending on what happened with the others.
Yeah, but if you substitute the hub, I mean, in the experiments, this hub is the mean field, right? It's coupled through the mean field. So if you put the mean field there, then it makes some sense because basically all of them are feeling the mean field. But in this case, I mean, it's basically, I think it's due to the fact that the noise of the signal that they're receiving is the same, and at some point it's so big that basically they are just feeling that. But that's.
Well, the difference, I think, in this point is that I agree that here is mostly noise, but here is this mean field from the other lasers, what is defining the dynamics of the system. So there is a change between a state where noise is mostly the driving signal. Anyway, you could remove noise here, and it's just to put some kind of perturbation at some point to turn on the lasers. Should work. And here are the other lasers that are the star lasers that are above threshold, that have stronger influence due to the amount of them that are injecting the light into the hub, that define the dynamics of the system. We also showed that with the cross correlations that the hub laser is always lagging the dynamics. So what is happening here is that the hub is always waiting for the signal.
While correlation negative doesn't mean causality.
Okay.
So,
Okay. So
Can you remind us what is KX, kappa X?
oh yeah. Going back to the case of the chemical oscillators, this X corresponds to the stirring rate of the catalyst particles in the Belousov-Zhabotinsky medium. So in the same way they changed the stirring rate of the system, changing from a smooth transition to a sharp transition. Here we can control the type of transition, smooth or sharp, modifying the pump current. So in this case, we can do a comparison between our system and the chemical oscillators, and the pump current of our system is playing an equivalent role to the steering rate in the chemical oscillators. In other words, the steering rate is modifying the amplitude of the oscillators from a quiescent state where they are not oscillating here, to an active state with certain amplitude where they are oscillating. And changing the density of the catalyst, they change it from an incoherent state to a coherent state. At this point, with this new model new old model that we have for the semiconductor lasers, we studied how depends this system, these transitions, as a function of different parameters of the system, especially what happened with the coupling term, the coupling strength, delay. Remember that those systems didn't have delay, so delay here is a new element in this type of transitions. So what we saw, first of all, is as was expected.
5 minutes is okay, or maybe 5 to 10 maximum.
Okay. The critical coupling depends mostly linearly with the width of the distribution of the optical frequencies. This critical coupling is a power law of the coupling strength, and that especially interesting, the time delay changes the minimum number of lasers in our system to synchronize, to start the synchronization. This is the case of Crowd Synchrony, the case of the smooth transition. So where we can see that for large enough time delays, it reduces the inclusion of these time delays, reduce the number of elements required in our system. So the time delay is good in this sense to have the synchronization for a smaller number of oscillators. So
there is it resonates with the natural frequency where the drop appears.
This is one of the natural frequencies of the system. In this case, the field decay rate of the laser.
But so inside the resonance, there is no change with respect to the number of the critical number of.
There are other resonances inside with other internal frequencies of the laser. So the second thing we did, and I will give just a general idea of what we did, is if we can find analytically the boundaries of this synchronization transition and how they depend on the parameters of the system. So what we found from this study, and focusing on the case of dynamical quorum sensing, the case of pump current below the threshold, is that we can find a double transition to synchronization, which means that we can go from an amplitude at the noise level to a sharp increase of the coherence of the system to a new level that is, let me show, the order of m squared, to a new transition for large enough number of oscillators in our system of the order of m. Okay? So two different but self-consistent large m scalings are possible in our system and can describe this first transition and this second transition independently, because they are self-consistent. They can be done in the same model but for different values of the control parameter. So I will not give you the details, but the main idea is we used a simplified version of the previous model I showed you, and it was, just the detail, it was recently published, if somebody wants to reference. The first scaling is basically rescaling of the electric field of the hub and the electric field of the star lasers in this way. So it leads to a constant value of the carrier number for the star lasers. In the other case, this assumption that the electric field of the hub and the star lasers is of order m0 with a certain scaling leads to carrier number equal to 0 or going to 0 for m large enough, which means basically that the hub laser becomes transparent. This transparency is induced to the injection of the outer lasers that reduce the number of carriers in the hub. So basically we can show now that the open circles, for example, that is for the whole model, can be here, for example, the open circles for the whole model can be well reproduced by taking into account the first scaling, here the red squares, in around the first transition, and the second scaling leads to this behavior of the equations. You consider an appropriate order parameter that tends to the same value as the complete model or the whole equations above the second critical value. So we show the type of distribution of the complex electric fields in the real and imaginary part for different number of lasers. We rescale our system to overlap these transitions at the same point, so we have general behavior where this transition occurs as a function of the coupling strength and the number of lasers and the width of the distribution. And also see that depending on how you scale the order parameter, you will find that in this region, for the three values I'm showing here of the number of laser oscillators, is almost independent of this m, but above the second transition, it's not. It can be because the scale with another factor above this second transition. So we found the analytical expressions. So the main idea is that we could find the critical value of where the second transition occurs and the critical value where the first transition occurs, and they are related with the pump current of the hub laser. Depending on the pump current of the hub laser, we could adjust the distance between these two transitions. So I'm out of time. So
you can just show the brief transparency for people to read well.
So as you know, the first two questions, there's priority for students who want to make a question.
Yes. In the initial equations, can you repeat them? Because the noise is put in the field, but if it comes from the stimulated from the spontaneous emission, shouldn't it be more natural to put it on the carrier equation?
well, you have noise in both, but the noise that comes from the carriers is much lower, much lower strength, and usually doesn't play a relevant effect in the dynamic of the system, and well, can be observed in the experiments, but this is the main source of
What is the origin of these noise?
Is the spontaneous emission of the system, the light that comes from the recombination.
Right. It's the photons that are emitted into the melting point by spontaneous emission processes.
And doesn't
And in fact, they should be exactly the same in the field and in the carriers, and the noise is exactly the same because every time a photon is emitted, there's a carrier that gets.
But you have additional terms.
No. But, the main point is that the noise, which the one of the spontaneous units should be in both places, and in the carriers there could be additional noise, but it is kept only on the field. Because in the field it is critical for the laser to switch on. Because we start with E equals 0, and in that equation, if you start from E equals 0, no matter whatever pump you put there, you will remain always at E equals 0 because it's an unstable fixed point. And noise plays a critical role in unstable fixed points. And the one for the carriers does not help you to go out of that unstable fixed points. So then that noise is typically neglected because a switch on, where the noise plays the most important role, is in the field. That doesn't mean that above threshold, once the laser is switched on, the noise in the carriers might be as important as in the electrical field, but it's usually neglected anyway.
The noise that is in the field. The noise is on the carriers. Because the field depends on the carriers.
But if E0, if E0, if you don't have noise here, and you put all the noise you want here, if you want to start with E equals 0, this is 0, this is 0, and this is 0, and this is 0, then you will remain 0. No matter what you do with the carrier.
Actually, in a more general term for the noise also depends on the carrier density.
Let me explain physically. If you have
Mr. Chairman.
to trigger the stimulated diffusion, you need a photon. If you have that photon, you don't trigger the stimulated emission.
So it's from the equations.
You need an initial photon that has come with this for spontaneous emission. That's the physical reason.
Leo?
Would like to see the quorum picture, please. Of your,
In the case
when you compare both. Yeah. So, what do you mean by this? Downwards errors over there.
Yeah, because the finite size effects take into account that here we only have 100 lasers. So it depends a little bit on the exact values of the frequency distribution you choose. You don't have 10,000 as in the previous case, as in the other case for the analytical calculations. You only have 100 lasers, so you have to calculate for different distributions and have a.
So you must start synchronizing in order to see synchronization, otherwise it doesn't spontaneously synchronize.
No, it spontaneously synchronized, including the first photon, the nice term. But depending on the distribution of frequencies, in the Gaussian distribution, if you, by chance, you choose the 100 values far from the central frequency, probably the system will not synchronize. So you only have 100 values, and depending on this value, it can change a little bit the exact value of the coherent intensity.
Okay. Some more questions?
Concerning the synchronization, the two synchronization transitions, I have the impression, correct me if I'm wrong, that only one is a real synchronization transition. and the other one is the sexual absorption condition for the hub. Might that be the case? Because the sexual absorber or the laser, the hub, at a certain amount of input will become transparent, and then you only get the coupling to the outside and the outwards. So that is one of the transitions you see, and then the other one is that real synchronization transition. Would you agree?
Well, would I why I say that those are two synchronization transitions? For example, here you have an increase of the coherence. This first increase is, as I understood, is the real synchronization. You said no.
No, that's the onset of coupling due to the sexual absorption in the hub.
Well, but this first transition also.
Certainly, that leads to a certain degree of coherence because it's a difference between having no coupling and having coupling.
Right, and why not? We can consider it as a.
Well, it's more a property of the hub than it's a property of the crowd.
Well, this. This property of the hub, you say, that is given by the crowd. Because
no, but the point is, if you, instead of the crowd, you have only one external laser, probably the same will happen, increasing the coupling with this one external laser. This is what you say. But it's perhaps not a collective phenomenon of the crowd. It's that there is more input and more power going in, and then something changes in the hub.
It's a threshold of the hub.
Is related with the threshold of the hub, as I showed there.
Certainly promotes certainly the onset of partial synchronization.
Well, it's something not really clear so far. If this synchronization or this first transition can be directly related with this only one element injecting to the other. But I think not. I think both of them are two steps to a more synchronized state. Who is the responsible of these steps? The existence of the hub is actually it's clear that it's important.
How much power you use to the hub?
Well, it's
that you scale with that.
But I think.
But there could be more to it, and it was a real question. I'm not sure.
No, I think that one of the points is also that at this level there is a dependence with noise, but not at this level. For example, if who is responsible of the whole star elements or the hub? If the star elements turn on the hub, who is responsible, the hub or the star elements? I think are the star elements that have a slightly larger bound current and start. They are the first who turn on.
Well, there's time for a quick question because we're already in the middle. Constantine?
Yeah, there won't be only one, so.
You can just start with the coffee.
Leaves the system. Maybe you should reinterpret it. Sorry, I hope it was not. I really would like to understand.